Okay, so good morning and welcome to the third Sunday of the month Chai and Why. Today, Chai and Why, recently we had Engineers Day in our country. So today it's as a way to acknowledge engineers' contribution to the science and society. Today's session is for Engineers Day special. And we have Dr. K.V. Srinivasan with us who is going to give a talk about very cool stuff. But before he begins, just for a formal introduction, he is a mechanical engineer by training. After completing his mechanical engineering, he did Masters in Engineering in Cryogenics. And since 1999, he is at TIFR. And currently, he is scientist in charge of low temperature facility there. And very recently, he also completed his doctoral thesis.
5 years back.
Yes. Okay, so that's not very long time. 5 years. And so today, he has actually been working on development of a lot of cryogenic stuff. Also, a local alternative to what is imported. So I hope he will talk some bit about it.
Yes.
Okay. So it will be very cool stuff on a very hot topic, cryogenics.
Thank you very much. Thanks, Ullas, for the nice introduction. Okay. Very good. Go to presentation.
No, Zoom, on Zoom.
Okay. Okay. I'll just start about mentioning about various cryocoolers, what you have been used here, right from the scaling, because that's what the whole objective is. From the large to the miniature, is there any possibility? So what are the advantages and how does it function? So we'll have an kind of an overall view of what is that's the name. Okay. Okay. So this the picture is which I wanted to start with this picture and also wanted to end with this picture. So for the connectivity, I just chose this picture. So here we can see the liquid helium plant as a master plant, and then there are some two cryocoolers which are at the bottom level, just to show the scale of what is what. All are doing the same job. One is that very large helium liquefier, which can produce 90 liters per hour. Okay, so for that talk emphasis, I just kept most with respect to liquid helium and liquid nitrogen, because these are the two cryogenic fluids used in the research purpose. Of course, it can be used for other purpose, but my talk will stick to this requirement of liquid helium and liquid nitrogen. And this is a large plant which can produce about 90 liters per hour. We have also a smaller cryocooler which can produce 20 liters per day.
People are not really well versed with cryogenic liquids. Tell them what is so special about liquid helium.
Okay. Yes. Okay. Okay. So, as far the cryogenic is concerned, the liquid helium, liquid nitrogen. So, for example, liquid helium, which boils at 4.2 Kelvin, that is a temperature which is close to minus 269 degrees Celsius. Now, normally we know that 0 degree at which water freezes. Now, if you want to go higher side, we can go up to very high side. Even the stars temperature are something like to 10 to the power 9 Kelvin or so. Okay. So, almost like an infinite range. Whereas when you are coming from 0 to below and life, and the entire thing stops at minus 273 degrees Celsius. So 0 to infinite and 0 to minus 273. So what minus 273 is a very precisely found thing, and which is practically not possible to reach. Is only a theoretical limit, what you call as an absolute zero. Okay. So now that whatever happens from 0 to higher side, which we know infinite, and 0 to lower side, which a lot of things happens, roughly about whatever happens at high temperature to certain extent, it will go to opposite way at the low temperature. So the whole interesting of cryogenics is that a lot of property changes at this small insignificant band of 0 to 273 compared to 0 to infinite on the other end. And of course, helium is at 4.2 Kelvin, it's just 4 Kelvin above the absolute zero. It's something like a helium element alone will remain as a liquid form. Everything you name would have been frozen at this temperature. Okay, so that is the lowest temperature available in the liquid form, so which is very widely used in the research aspect. So that's a very good. So when you talk of, when you are trying to produce liquid helium, almost everything would have been frozen at this temperature. So if you want to liquefy, you have to take care of all this process in the impurity or any kind would have been freeze this whole system and will take long time to rectify, clean and redo it. So the liquefaction process is highly complicated in terms of temperature, because as I told that everything would freeze at that temperature. So in that context, that if you are going to see the emphasize with the liquid helium, and the large liquefier can produce 90 liter per hour, whereas a cryocooler, what we are going to see is some 20 liter per day. Okay, so there is a huge reduction in sale. So now other one which is a little smaller, it's about 5 liter per day. So now what you are trying to come back is from 90 liter per hour from hour to the small scale, because this kind of a scaling we wanted to. So you have to, the whole objective, you have to come down or basically get down to the ground level to see that such a kind of a very low, small compared to this kind of a commercial plant, because all the things are available in TFR. So in that sense, we will come down also from the ladder as from the objective part, how these cryocoolers can be used or how does it function, everything. Now, when we are thinking about this format, it's always a big better, because as you see the huge jump from 90 liter or a huge reduction when you go to the cryocooler. So is it really the size matters? Are these very more important where the quality or the size? What do you, how do you select, on what basis? Whether the physical dimension makes any sense, whether the quality hasn't some compromise with the quantity. So these are the things which we would like to see at the end of the talk. So what you may learn today is what is a cryocooler, why do we need it, and how does it work? Because that's a basic thing which we want to do. My objective today would like to make it what you may learn, that I should say my success in getting that what you will learn today. So this is what my wish to have this talk at the end of it. So whether it is still I'm able to fulfill or not, which we'll see. Okay. Now we also need to know what is a cryocooler. We just go by. I'm not going very deep into the science. I'm not very bypassing the thing. I'm trying to explain the principle so that you will able to understand end of the day that I have seen the cryocooler, I know what is the function and this may be of this kind. So we'll have some overall idea at the end of the day, because that's a whole objective of my talk. We know that this normal refrigerator, and refrigerator nothing but some cycle works at the back. We have a compressor, and then we have a condenser coil, then the expansion device, and you get the cold temperature here, which will about here in the refrigerators maximum minus 20 degrees Celsius. So that is what you get in. So the background of this refrigerator, there is some cycle, or the gas cycle is operating. It is in a closed cycle, so that whatever there is compression, expansion keep on take place, you will get continuously the lower temperature. So whatever that when the low temperature is there, you can keep your stuff and cool it. So that exactly the whole objective of thing. The cryocooler is also called a cryo refrigerator. Is some cycles produces temperature which is much lower than what you is that. So it's close to minus 150 degrees Celsius and below, what you call the 123 kilowatt. So that is what you call as Kelvin cryogenic temperature. If anything would have been higher, they will call advanced refrigeration temperature. So what we are going to see is in this vicinity how that cryocooler works. So we'll see how does it work. So it is exactly like a refrigerator, some cycle working, and these most of the components are more or less same. The compressor, expansion, all the things are same. Let's see how they. Now, before we go, whether what is the thing, we need to understand what is the real need of it. I mean, really, is it very much essential to have a cryocooler? Need to understand how does it function, what is all about. Let's see the application, then we get more interesting to get to know how the cryocooler works. So large liquefaction plant, as I said, it can be either for liquid helium liquefier, which has 4.2 Kelvin, minus 269 degrees Celsius, or we can liquefy as a liquid nitrogen at 77 Kelvin, about minus 196 degrees Celsius. So for the liquefaction plant, we can use a cryocooler. There are some also called a re-liquefaction plant. So if we have an cryogenic fluid sitting inside, everything after some point of time, it's keep on evaporating because it's very, very cold and things keep evaporating. And once it evaporates and it will go away, and then you have to refill the system again with the liquid helium or liquid nitrogen. Assume that if a cryocooler is fixed on this top of it cryostat, whatever the boil of cold vapor comes in, we re-liquefy it or recondense it, so that put it back. So once you start with an liquid helium, and then after that you don't need to refill the container system at all. So the cryocooler will keep on recondensing and put it back, so the system can go on. So what you call as a cryogen free or ever cold system. So all the things which is used with liquid cryocooler based. So cooling of thermal radiation sheet, which is one of the application. For example, we know that the heat inlet coming into the cylinder is by conduction, convection, and radiation. So by evacuating, we almost remove the conduction and convection, whereas the radiation, it can still go through the vacuum level. To avoid it, we do reduce the radiation shield. So radiation shield, we know that the radiation heat inlet is Stefan Boltzmann T to the power 4. Okay, so that is the way. If the T is less, the radiation heat inlet would be much lesser. So if I have the heat is coming from the atmospheric to 4.2 K, I put some shield and which is cooled with liquid helium or liquid nitrogen or whatever the temperature, then the T to the power 4 is reduced. So it's used as a radiation shield to preserve the inner temperature. Either it can be 80 K to preserve 4.2 K, or maybe much different location. So base radiation shield is to have to prevent the heat inlet in a very, very large scale. And this can also be used for cryo pumping. So if you want to reduce the pressure of a chamber, for example, space simulation chamber, we used to test the samples. What will be the scenario at the space? You have to recreate the system. Here, the space simulation, the vacuum is much, much higher, which is normally not possible, but most of the pump. So when you pump below 10 power 5, 10 power 6, 7, 8 millibar, but it is space is something close to 10 to the power minus 12 millibar. So to achieve that, what you need to do, you cannot really pump down the gas or really freeze the gas or condense the gas, whatever trapped in the volume, by cooling it so cold that you reduce the pressure of the chamber, so by which you can create the high vacuum. So cryocooler can be used for achieving a very high vacuum thing. And many of these astronomy detectors, sensors, optical instruments, to have that working sensitivity increased, the thermal noise has to be reduced. So basically, if the infrared is nothing but the heat coming to heat signal, so the red wavelength is close to that line. So to reduce this noise, we cool the sensors or the optical instrument to sufficiently lower, so that your thermal noise is substantially reduced. So that is what one of the things. And when you go for a smaller cryocooler or a miniature type, what we are going to see in that, it can be used for the missile system, night vision system, infrared thing, and also the guidance system, surveillance system. So the most of the strategical application that they use for a very compact, because it can be mobility is very, very important there. It's also used in electronic device chip or the memory device, or called the energy storage system, which also sufficiently requires a very low temperature, which can be fulfilled with the cryocooler. So that is a huge application of cryocooler or the low temperature in overall. Okay. So now, if you want to know the application is there, we would like to know that how does it work and what are the things. So to know that how does it work, if we go there, before to that, we need to understand what are the different types of cryocoolers. So once you know the structure, then it is easy for us to know. So cryocooler, which this for particular temperature, we can use these, these kind of a cryocooler will have a different application, all those things. So these, there are 4 types which we are going to see in the course of the lecture. Is the Joule-Thomson cryocooler, and then other one is called Stirling cryocooler, and then third one is called Gifford-McMahon or GM's cryocooler, or pulse tube cryocooler. So these are these 4 variation you will see which comes under the cryocooler category. Now, before moving into those different type of cryocooler and different types of cryocooler, I just want to know that you have seen this picture, no? So this James Webb Space Telescope, and this is in orbit now, taking a lot of pictures and I think you know that this position of this James Webb Telescope is in a very, very particular point. So what they call this Lagrange point 2, that like, so it is something like 1.5 million kilometer away from the Earth, thing in between the moon, Earth and Sun. So basically, this has been kept because this wanted to study about the infrared wavelength and the study of it. So infrared means that heat is a killing element. So we wanted to protect this James Webb telescope from the heat. The best way is to avoid the sun or hide behind Earth. Okay, so the hide behind the Earth we said only option because these are all the 5 points where it's Lagrangian points. It's nothing but that if you put any telescope or any orbit or any of the satellite, whatever it is, it doesn't need energy because this particular, the Lagrangian point is nothing but where the pull and push is equal. For example, if the point 2L, it is there, it will be keep on roaming within the perfecting the sun, the Earth without moving, either go away or come inside. Because if you put it correctly in the space, it doesn't need anything. The push and pull is equal. So as long as the Earth moves, it keeps on moving along with that. So you don't need anything. You don't need any fuel to do that. So this point is that it can be put in L1, L4, L5, L3 because all these portions are exposed to sun. So which is not required. So this is the only point which is available for this James Webb Telescope to do that. So that is how it has put that. Because it's going to study the infrared sensitivity of the instrument. So that is the main objective of it. As I told, that infrared means that the signals what is coming as a heat, and we want to have much more better clarity in doing it. To have the study, it should be away from the hot surface. So primarily it absorbs infrared light, which sometimes felt as a heat basically. So the telescope has to be very faint, receiving the very faint signals from the distant object. So any heat keenly coming into the system will don't know whether it's a thermal noise or from the source which we wanted to study. Okay, so that is a whole objective of it. Now, even though this is hidden in behind the Earth from the sun rays, obviously if you see the temperature, and here it is the shield, you know that there's a size of a 3 tennis football ground size, the shield, and one side of the temperature, even though it is hidden, is the most ideal location. The temperature is something like 358 Kelvin or something like 85 degrees Celsius. The other end of it is 40 Kelvin, minus 233 degrees Celsius. You know, there is a huge difference in this temperature, even though it is an ideal location. But to protect this happening, you say one side is liquid water boils, other side liquid nitrogen freezes. Nitrogen freezes. These two ends are so quite the thing. So to avoid the heat in leak, they have, even though to get this temperature, they put 5 layers of radiation layers so that you try to get it. But still, this is not enough, because these optical sensors has to be cooled much below, and in fact, it has cooled down to 6.3 Kelvin using a cryocooler. Okay, so the cryocooler, which has a built-in cryocooler is there, that will supply the refrigeration, which will cool all the optical ends. Eventually, it cools up to 6.3 Kelvin. So there's a huge application. It is sitting. This is the actual size of the cryocooler, which is in orbit, which is in working condition, because you choose this cryocooler. What they use is a pulse tube cryocooler. Let us see those things. So these cryocoolers are almost like, you can't do any maintenance. It has to work high reliability. The robustness is to be very, very high order. So these are some of the area which cryoCooler is used very, very substantially, because know that order of reliability is what proves that why this is being used. Okay, now just we'll be going back and forth in the cryocooler part, so that to get more control of the subject and then in acceptance part. So we'll start with the first one, Joule-Thomson cryocooler. So Joule-Thomson cryocooler is nothing but we have like a refrigerator, right? You have a compressor. We will compress the gas from 1 to 2. And once you compress the gas gets heated up. So you pass through the heat exchanger. then pass through and called Joule-Thomson wall. So Joule-Thomson wall is nothing but the high pressure gas is allowed to expand without doing any work. It's kind of free expansion. So thermodynamically, they call it as a free expansion or isenthalpic expansion, where the enthalpy remains constant. So due to the change in the energy, that high pressure gas, when it gets expanded, the temperature gets lowered. So this is called the Joule-Thomson wall. They also call it as a Joule-Thomson. It can be a capillary tube, or it can be a fine porous plug, or it can be a needle wall of any other kind. Okay, so those all the thing is to have a fine regulation of flow, which will lead to very low temperature. So these processes are called Joule-Thomson expansion. If you the cryocooler employ these kind of techniques, we call the Joule-JT cryocooler or Joule-Thomson cryocoolers. Okay, so very simple example. This also called Linde cycle. The same can be scaled up to produce 100 liters of liquid air or nitrogen per hour also. Okay, so it is the cycle is same. You can scale up to the level you want, or you can go to the miniature level also. So in the cryocooler, what we are going to have is more, we are going to emphasize about the miniature cryocooler, which implies this kind of a thing. Now, how does it actually work? If you want to have a miniature cryocooler, it can't have a compressor, we can have a heat exchanger, everything. Instead, I say I have a small bottle which has a very high pressure. Gas is allowed to go through the heat exchanger, and then it expands in the expansion wall or the capillary tube or Joule-Thomson wall. Once it gets expanded, we produce some low temperature, and the cold vapor which is going out will be cooling the incoming gas so that the cycle efficiency is improved. So if we want to have a very long coil in a very short duration, we want to have a spiral or helical coil of that. So nothing but something looks like a fin type helical coil. So that gas will be passing through that inside the coil, when get expanded from the bottom, and the cold fluid will going out, and the fins gets cooled. So that's how the size is. Now we see the size of it. Okay, the tube diameter is 0.3 mm. And the diameter of the orifice, the Joule-Thomson wall, is 0.1 mm. The entire length is 2 inches. It can produce up to temperature of 70 Kelvin to 100 Kelvin. So these kind of small cryocooler, miniature cooler can be used for the optical sensors or the thermal imaging camera. We will see some of the application in which can be. So the problem is, not the problem, it's the advantage of this small cryocooler is can be sized down to any level we want. You know, it can be even goes to 1 inch, less than 1 inch. All the things are possible. For example, this can go, the pressure what they use is 420 times the atmospheric pressure in a small capsule. In fact, this previous one, the capsule, what we are having is 100 ml. It's such a tiny capsule, and it can be replaced. You can unscrew, connect then another small bottle of 100 screw. That's how we can do that. So here in this one, we can reach up to 80 Kelvin using air, which is filled with about 420 times the atmospheric pressure, and the size can be small bottle of 100 ml, few ml, whatever it is. Okay, so it can be even go to, they use the argon gas with a 400 bar, but these are all not continuous usage, because if the compressor means continuously you will be supplying the high pressure, but here the bottle is some for a timely use. So this can be used for some kind of a missile control or this kind of a very task-oriented object. So this can be used for that. Okay, so this is the background of all the cryocooler. Now we'll switch to Stirling cryocooler, because this is the base for all the remaining 3 cryocooler. So this all we call as a, like I said, it's a cryofrigerator. The refrigerator will produce some temperature close enough to minus 196 or even minus 269 degrees Celsius, so that we can liquefy hydrogen, oxygen, nitrogen, air, helium, whatever it is, depend upon the temperature what you produce. So basically, the surface, the cycle will produce some low temperature. When the gas comes in contact, either it may condense, it may cool, or it may freeze, depend upon the temperature what you get it. So this is how the cycle is there. So in a cryocooler, we need to understand a few components and then objective of it. So we may be normally seen that heat exchanger. Normally we see heat exchanger, the hot fluid will be flowing in one direction, and cold fluid, the fluid, we want to reduce the temperature, will be flowing in the opposite direction, or the cross flow, whatever the. So both will be flowing together. So the thermal barrier in between these two hot stream and cold stream will be transmitting the heat. Okay, so this will be a continuous process. So what you call as a recuperative heat exchanger or normal heat exchanger, shell and tube heat exchanger, plate fin heat exchanger, all these heat exchanger, they are all called recuperative heat exchanger, is nothing but hot fluid and cold fluid flowing continuously. Now we are coming to the regenerative heat exchanger. There the hot fluid is moving from one end to other end, then it stops, and then some other fluid is coming from the bottom in the same direction, same is coming from the bottom. So it will be either coming from top to bottom or from bottom to go. It's not together like here. So it's kind of a pulsating flow. The gas will be coming down, going up, something like that. So there's a pulsating flow will happen within this part regenerator. So we call the regenerative heat exchanger. So we will put it in a simple term, it's a regenerator. So this is what the word we will be using in all the cryocoolers. The regenerator is nothing but these are all the regenerative heat exchanger matrix. It can be filled with some various matrix material so that temperature can go in and then come out. We'll see how does it go. So these are two terms we need to understand. Now let's see how a Stirling cryocooler works in a simple term. We know that like it's a closed mass, the gas is not, it's not going out like a normal refrigerator, whatever it is, the freon gas is circulating. Here some working fluid will be going through it. The gas gets compressed in a compressor. When the gas gets compressed, the heat is generated in the fluid, which needs to be cooled so that you can use the air cooler by which that heat of compression is removed, or by using the chilled water or the normal water by that, so that the end of this process, the temperature is brought back to atmospheric. Of course, the pressure has gone up here. Now, the high pressure gas is passed through a material called thermal bank. Its thermal bank is nothing like, now if I want to understand it, that if it pass through it, the bank is something it can store the refrigeration. And whenever I want, it will give me a refrigeration. So it's a bank is that the gas will flowing through this, the hot atmospheric temperature gas, high pressure gas pass through the heat capacitor. It goes throughout for the moment you are going. So it goes out of the thing. Then you go to the next process called the expansion process. Okay, when the gas gets expanded, obviously we know that temperature gets reduced. Now that reduction in temperature, the pressure gas going into the regenerator or the heat capacitor in a reverse way, and all the refrigeration it produces in the expansion process get captured in this regenerator, so called that thermal bank. So all the refrigerator is captured here. So when it out of this heat capacitor, it is a room temperature gas. Again, the cycle goes here. Next compression takes place, and then when it goes inside this heat capacitor for the second cycle, the gas when it comes out would have been cooled because of the refrigeration what it stored in the previous cycle. Okay, so it gives out the refrigeration. So the gas after the exit would have been slightly colder than what it was in the previous cycle, which is further cooled in the expansion process, and the refrigeration gets captured here, and the next cycle it will be again further cold. So the temperature outlet here will be keep on cooling more and more, because and the expansion process will go to further cooling at this end. So ultimately you reach an ideal or stable temperature, a very low temperature at this expansion process. So this is the process by which you get a cryocooler. So the entire process where this cold thing happens, so it just insulated externally so that there is no heat in leak happens into the system. The performance of this cryocooler is highly dependent. In fact, that is the only component which decides the performance of the Stirling cryocooler. As such, is nothing but the heat capacitor, what you call as a regenerator, the regenerative heat exchanger, as we have seen that going either this way or coming this way in a pulsating flow. So if the compressor is working in a very high speed, it may be going something like 36 hertz to 50 hertz, depending upon the way we are pushing the heat. So it's a pulsating flow happens within that. So these heat capacitor design is highly complicated. We will see how this is important. Now, somehow we have a regenerator. The whole object to be put into kind of a commercial cycle so that it can produce low temperature. So the Stirling cycle initially, in fact, the older time, all the cycles were made to produce work from steam. Okay, that's the whole objective in long back, in 18th century. Now, In 1834, John Herschel, he has modified the engine to use it in a reverse way, put some work and see how does it expand. So it's a reverse Stirling cycle, and this becomes so popular that becomes a Stirling cycle means it is a low temperature production cycle. So it's no longer been used as a work producing cycle. It is actually a reverse Stirling cycle. Now has been reversed, and it becomes a Stirling cycle. So now this is happening. Now what happens here? How does it work? We have a compression, there's a piston here, and there is one component we call as a displacer. The displacer is a floating piston moving up and down. So in between this piston and displacer, other part is sealed, and annually I kept that water cooler and the regenerator here. Now let me explain this process. The gas is charged here, the working fluid. Okay, the working fluid is charged here. When this piston moves up, it is already on the top end. So when the piston moves up, the gas volume is get reduced or it gets compressed. So when this position comes in, all the gas would have been compressed here. Now, since it is on the top, nothing can go above. And when this floating piston, the next cycle, that alone comes down. This has already gone to higher end. The floating piston is coming down. So it pushes the high pressure gas through this water cooler, through the regenerator, going to the other end. That's what happens there. When it pushes the high pressure gas, the gas flows through the water cooler, through the regenerator, coming to the top space. Okay, so the next cycle, both the displacer and the piston together comes down. So that means that the gas which is there, the high pressure gas which has gone from this place to that place, it gets expanded. Now the gas would have been cold here. Now the next cycle, this remains in the same, and this alone going up. So it pushes the cold low pressure gas. That will come in the reverse way, cooling the regenerator through the cooler, comes back here, and the cycle starts. So the next cycle, when the gas goes from here to here, the gas would have been cooled here because of the refrigeration captured here. So this how what you call as inline Stirling. So everything is in the line. So piston, compressor, everything, regenerator, everything is there by which you can produce flow. So this works in a very high speed, about 30 to 50 hertz of operation, the cycle by which you will produce a low temperature, which is what you call the cold head. Okay, so that portion, what you call the cold head, is the normal slang, but they use is cold head, nothing but the spot where you get the lowest temperature. It may also called a cold finger. When it becomes so small, we call it as a cold finger. Okay, the same thing is explained in a little animated way, so that the compressor and displacer move in a different synchronized. It is not together, because one portion it goes up, next portion comes. So this operation has to be synchronized in a kind of a cam operation, so that the gas gets compressed and pass through the cooler, pass through the regenerator, goes to this top end, and this gets expanded. Now, if we want to plot this operation from the room temperature, it goes to compression space in a compressor. Once it gets compressed, and then pass through the cooler, then it goes to the regenerator. In the first cycle, the temperature is same, because it is already, we are starting from time 0, and then it gets expanded to T1, that the cold gas comes here, and then it goes here. So if you see here, and the next cycle, it further goes down, and then goes up. So we are concerned in the regenerator part. As it keeps going down and down, so the temperature gets lower and lower here, whereas the temperature at the exit of the regenerator is constant at regenerator. So it means that you are not allowed to lose any refrigeration going away. If this regenerator is there, it may skip, then you will lose the efficiency of it. So the criticality of the regenerator design is what I wanted to emphasize, is that, and this will come why it is important in designing of all the cryocooler. Okay, the design of the regenerator, because it is the heart of the plant. So if it's a typical plant, which we what you call as a Stirling cryocooler or Stirling cryo refrigerator, this produces some large scale liquid nitrogen. I have a So this, if you see that synchronizing, how does it moving up and down is come by the cam operation is done by the thing, because these are all mechanical component which you can design at what the whole timing diagram or the phase sequence diagram by which you can design the whole thing. So this is the displacer. It is just a displacing from one place to other place. This is the piston. The compression takes place here, and the actual cut view of this diagram is shown here. And if this temperature is produced at this thing low temperature, I supply some nitrogen gas here, it goes there, it gets liquefied. Sorry, gas is coming here, it gets liquefied and flowed through out of this unit. So by which I can produce liquid nitrogen, and the temperature is much lower, I can put helium gas and gets liquid helium out. Or if you put air, it can come out. So it can be used for any application, depend upon what is the temperature or what you get at the exit of the expansion space. Now, in the commercial liquid nitrogen plant, if you see that what is a water cooler, regenerator, piston, so many components are there, just to know, that complication of it. Okay. Now, with this cryocooler based cryo-refrigerator bed, TFR has a history of liquid nitrogen plant from 1968 to current running plant. So this is the very old plant which can produce 30 liter per hour. So instead of one engine is running, you put 4 engine together. So 4 engine will be cooling in a phase difference of 180 degrees. So by which we can operate more liquefaction plant. Then with the next plant was in 92. Then again is a 30 liter per plant. Earlier the name was Philips because Sterling Cryogenics was cycle name. Philips is a company was manufacturing, that later it has been changed to Sterling Cryogenics. So currently what we have here is that 2 set of 4 cylinders. So 8 cylinder operating, we can produce 120 liter per hour. So this was 30 liter. Now it is 120 liter per hour for 2. Basically it is 66. The 30 has gone to 60 with the latest all this improvement happening. Now, in all these things, we are assuming that the cryocooler regenerator is working very fine. So what is the condition of design? If you want to design or you want to fabricate, what are the design criteria for this cryocooler regenerator is that it's a temporary storage. It stores and rejects. Okay, so it will be quickly capture and quickly to give up. It's very difficult to design in the sense that an ideal regenerator should have a very high thermal capacity. It means that refrigeration comes in, it should have a capacity to accept it. So what you call as a volumetric heat capacity. Assume that you have a sponge, you put it in water, so it will soak whatever the capacity is. After that, it can no longer can soak. But if you go for a different type of soak, you can get more quantity. So that volumetric specific capacity is nothing but the capacity to capture the refrigeration. Okay, it's a so we need to have very high thermal capacity. It's what we are doing. Endless. And it should not be passed through a small portion, and it should have any unused space should not be there. Otherwise, we lose the refrigeration. It need to have a high heat transfer area quickly in a very short time, and it should not have any loss. When you pass through the thing, it should not have any loss, because when any restriction happens, there will be some pressure loss. You should not have a pressure loss. It should not have any unused space. So these inherent parameters are so completely contradictory. It's very difficult for us to design a practical Stirling regenerator. Now, I'm not going to this detail for the moment unless you are specifically interested. What I want to know is, if I make a regenerator, how effective it is. I want to find, if I want to have from room temperature, I want to go down to that certain temperature. How do you find the effectiveness compared to an ideal condition? In the ideal condition, whatever go in, everything will be captured, but obviously that is not possible in practical. How close is the practical purpose is that? So what you see here, when I compare the heat transfer with an ideal condition, for this is the effectiveness. If it is a 1, then there's no loss is there. But if it is 1% is the loss. Is that anything? Okay. So if the 1% is the loss of the effectiveness, it is 99%, then you will lose 21% of the refrigeration, what it can capture. So if you put 100%, if it is a 99% is for a design capability, but you can able to do only 80% of the refrigeration, 20% is lost in the whole operation. But if it is in 98%, almost half of the refrigeration is lost. Then if it is 95%, it is just a useless product. Okay. So this shows how critical is the regenerator effectiveness to decide it. So a typical regenerator in commercial plant or any of these plants should meet these criteria of 99.7%. Okay, so this is highly, and for your comparison, if you have you must have seen many of the heat exchangers, plate field heat exchanger, shell and tube heat exchanger, even the plate field heat exchanger is most effective compared to all the things. These are all something close to 84% is the maximum, okay, currently, and the top high efficient thing. But here we are seeing 99.7 is what the grade. So the requirement has been scaled up enormously high, which is highly impossible to do that. But this is how the cryocooler works. We know that regenerator is the common. Now, what is the material is used for the regenerator? It can be like an annular gap regenerator where the gas flows through the pipeline. And other one is called the wire mesh screen. So, one wire mesh. It is not the screen. It is just one above the other. So like that, it can one wire mesh. Or you can use the wool as such, you know. And then you use the pellets or small granules to pack it. Or maybe the dimple ribbon where have that gas will flow through the dimples, and also have then foil type. These are many types are there. But this is an actual cut view of an old Stirling liquid nitrogen plant regenerator. The size is something like, you know, about 100 mm dia and 40 mm is the thickness. So now we are seeing that the gas going at 300 K comes out at very low, and every time we ensure the lower temperature will keep on going lowering up to something like 65 K. So the delta T across these 40 mm is something close to 200 K. So it is very, very difficult to maintain. So this size, you have to maintain this heat in leak such a way that you don't lose any refrigeration in a very, very short period. So all the time it comes out will be of thin average. Okay, so there are gone to different type. The initial plant was used a copper wool, and it is so tightly packed that what is called the packing density, or we call as another terms called the porosity, means gas has to flow through the plane. So how much is the porosity? Is that it means that typically that it is about 69% of about 69 to 70% is a porosity. Means if I put is a solid block, it is 69% whole intact. Okay, so it is but it is so tightly packed, it is very impossible to feel that it is 69% or 70% is open is that. So it has gone to many level of design by the Stirling cryogenics. Then the current one, what we are using, the oven type regenerator. Materials also change. This is the stainless steel regenerator. So if you see here, this is existing oven type, 100 mm dia, 50 mm height, and it is shielded with a cover. You remove the cover, then you can peel off each layer of this woven wire mesh one by one. So many layers have been stuck together, compressed, and the gas will be flowing through that. And if you can open a single layer and do the study, and we can say it is something like, you know, it's about 80 micron by 30 micron is a grid size. So many, and you can see this is actually the original SEM image of woven wire mesh. Okay, so the quality of the size and the stacking of so many layers and in which the gas flows. So this is how something in this size about 2000 to 3000 layers have been stacked roughly. Okay. All these things, previous work, what we have seen is for the liquid nitrogen liquefaction, which is similar to what is the plan what we have. Now, we also wanted to go temperature much lower to liquid helium temperature. The copper or the stainless steel or copper wool or copper woven wire mesh are no longer used. As I said, that after a specific volumetric specific capacity ceases for the temperature, because depend upon that you have choose the material. So there are so many materials. If you want to go below that, you have to use a rare earth element, to iridium, those kind of, even the lead can also be used, or you can use the partly SS, partly lead, or the combination of the hybrid regenerator. So many types are possible, but all the liquid helium temperature production cryocoolers, they all use this rare earth based material than these things. So depend upon the temperature, you can choose the material by which you can do that. So this was the previous research by us in developing a regenerator by for the similar plant, so that it can retrofit to the existing liquid nitrogen plant. So this was not built with the woven wire mesh. We know how that has been, but we want to do it in a 3D printing. So the 3D printing, people will know that what is a 3D printing. It's a layer by layer printing. Okay, so that's the whole technique of it. For example, how this it is on the powders are being fed. The laser beam will melt each layer, and once it is each layer is melted, the next layer of powder is filled, and then again it melted. So each layer is been built one above the other, and like that the whole product is built in the way. So this is actually the in the metal 3D printing, what you call the additive manufacturing. The 3D printing is a very generic term. When you are dealing with metal 3D printing, we call this additive manufacturing. Okay, so that's a so by which you can do it. So our one of the what we had taken is to build the material using the various structure of granules, something like, BCC structure of small 1.2 by 1.2 square, by which you make a lot of modeling to make it in 3D printing. So this is what I say, the porosity was 69%. We are like to match more or less similar to that with various technique. And then this is the first ever prototype made in 3D printing. This is the only product which is ready to use. People must have used it as a part of some component, build it, and then do remaining part. But this is the ready make, take it, use it in cryogenic. So that is how the thing. So what we did is we made all the signs, dimension, everything similar to what we need so that we can take it and use it in our product. So this is actually, we use this product, this is an actual printing video of this our product, which used the SS316 powders of 20 to 50 micron granules, average size. And then each layer was printed using the carbon lasers of 400 watts in a machine. So normally when they print it, they also make it a small test piece so that you can see, study everything. So basically the entire CAD model is given into a software what's called the slicing software. It will make it into different slices, and then each slice the computer will turn into the program, and each slice that much granule will be melted using the thing. Okay. So it goes with this it's random way. So it's a bit slow printing, not so, but it is a ready-made product compared to that. Okay. So now what we did that we just take it out from the bed and then cut it off the product and do the cleaning with various removal, because some parts would have been melted, some parts would have not melted, would be trapped inside it. So by various method, we clean this excess powder and can be readily used. So this actually the existing wire mesh is extremely replaced with the similar size and similar properties using the additive manufacturing. And this took about 1348 layers printed and about 53 that's the final thing. And it took about 44 to 47 hours for the total printing. This thing, and the cost has been 1/10 or low compared to the original one. And so this was also taken for testing. And this testing has been done in a single cylinder machine, because we have made only one first prototype. So you have a single cylinder machine. What we have is 4-cylinder machine. Okay. So single cylinder machine we were tested, and it was going to up to 99K. And there was some room for liquefaction. Of course, it was liquefying air close to that. We have changed various pressure and other formalities by which we are able to prove it. So this was the first product ever as a ready-made off-the-shelf used for the refrigeration purpose. Okay. So now, again, coming back to that, we know what is the Stirling cryocooler. Now we move to the next one, is called the GM cryocooler. So it's called the Gifford McMahon cryocooler. So it is exactly the, as I said, the Stirling cryocooler is a base cycle for that. This also Stirling cycle. It's something like, if I put the earlier Stirling cycle as a window air conditioner, and this one I will call it as a split air conditioner, is exactly the same. So here, in the old version, the compression, expansion, everything takes place in line. Here, I take the compressor out of it, and compression takes place, and only take the two lines of the high pressure and low pressure coming to this cold head. And this only the wall operation will move all these heat exchanger that will come out, and the return gas will come to the compressor for suction. And so this will be cycle here. So this basically to avoid the vibration coming to the cold head. If you want to do some experiment, this will be too much of vibration in the previous cycle. Here the vibration part is isolated. Okay, like exactly like your split air conditioner. Okay, so it provides high flexibility. It can be taken out of the room, or it can be far off, 20 meters away, whatever it is possible. Okay, so now we like to know how does it work. And the only change here is that in the previous cycle, we say that there is a displacer will be pushing up and down all the gases. Regenerator will pass through the regenerator. Here, the regenerator is sitting inside the displacer. So that is the one change here to make it more safe. Let us see how does it work. So this is actually the cryo pump unit, what you call as the cold head. This is called as the cold head because this portion where you get the lowest temperature connected by the flexible hose line to the compressor, which can be away. Now let us see how this works. Okay. Now we have a compressor. There are two walls. So from here to here, it is sitting in this cold head. Okay. Now at the point the high pressure gas, this wall gets open. The high pressure gas is coming here and passing through a small annular hole, passing through the regenerator. Regenerator is this one, and this is the displacer. And pass through the regenerator, comes out here. And since this is a high pressure gas, it comes here and pushes this piston up. Okay. So it comes up. Okay. So as it keeps coming, the gas will come up and it's slowly moving up. Okay. So the gas from cycle has come down. The next cycle, that whole thing moves up and it gets expanded. Gas gets expanded. So once the gas gets expanded, now again it is coming down, pushing the cold gas through the regenerator to the top of it. Okay. So now here the displacer movement, wall opening movement has to be synchronized. Earlier it was part of it. Here, this during this process, this has to be open, this has to be closed. So the wall sequence has been done separately in such a way that all the openings and closings are made, and you can make a two-stage cryocooler. When we want to go for 4.2 Kelvin or helium liquefaction, single stage will not happen. So you have to go for two-stage cryocooler. Then it's exactly same. This is a cold head, and this gas, the first stage outlet will go to the second stage of this cryocooler. Okay, so the process remains the same. The cold head will come and we will get the lowest temperature here. We do get a low first stage temperature here, low temperature, and then also you can either take, you can put a tap and then take the temperature from the first stage, or you can take from the second stage, or both, depend upon the need of it. Okay, so now we want to use these two-stage cryostorage. One of the applications which we have mentioned for cryopumping. Okay, if you want to have a space simulation chamber, the two-stage cryocooler is fixed into this chamber after receiving some basic vacuum by traditional mechanical pumps. So this has the first stage here. This is the second stage here. And we take a tap of first stage here with the shroud as a radiation shield. So this shroud will come. When the gas comes in, this temperature is close to so when the gas comes here, the temperature here is much colder. Then gas gets all the region, and then it goes to second stage. This temperature again, the thermal string is there. So it is pre-cooled with this thing, and the next stage here. So by this way, all the vacuum gets sucked and the gas molecule gets sucked in. If it is an condensing with the 80K, it will condense here. Otherwise, it will pierce through here and then get frozen in the second stage here. So this how that works actually. And this wall operation is done by a cam operation. Okay. So, and this connection will be connected to the compressor, and these are the regenerator here. Like exactly this is the first stage, and first stage is connected to the number to have this thing. And the second stage we go to 20K. This is how the construction is there. After some, to enhance the evacuation, what they do, all these places they put some charcoal absorber so that when the gas comes in, it gets condensed or frozen where it is going to sit. So you put some charcoal in it. So charcoal is a bed absorbent. It gets absorbed and trapped in the charcoal. And then after some point of time, you heat it, and then it evaporated. You can pump it out here. So this how you can trap the gases can be used here. And this, if you want to use for the very high vacuum, depend upon the temperature, you can use for the higher vacuum. For example, if you want to go space simulation of -12, you will have to go much below that. For example, if I have this 60K array, all my moisture would freeze, but where the nitrogen, argon, hydrogen, neon, helium, everything would pierce. If it is my 20K, that nitrogen and argon would freeze, where the hydrogen, neon, helium would go through. Putting that here, of course, this is what you get it. You can go further down also, about 3 Kelvin also, but this is the maximum you do it. So this is called the cryoabsorption pump or a cryopumping, by which you can achieve very high vacuum. Okay, so this is some of the old video which my friend Vijay Arolkar has dismantled. This about goes to up to 10 Kelvin second stage thing. So you say the dismantle, you can see that how the cam operation works here. So this only showing the regenerate displacer inside which the regenerator is there. And the next video I have about the cam operation here. So this how that wall sequence of opening and closing and then movement of the displacer is done through the cam operation. Okay, so this basically the GM cycle. So that is very, very widely popular and can be used even many of the applications are there. We also have an latest thing about the pulse tube cryocooler is exactly again the next version of GM cryocooler. We wanted to further reduce the vibration here because many of the sensitivity equipment, scientific equipment or detectors can't have even a single very low vibration will also kill it. To avoid that, here also the gas going and coming and the piston moving is happening. There is some vibration. Of course, the compression vibration, which was compression, that is isolated. But the movement of piston, everything will have displacer has some vibration. To avoid that, the pulse tube thing has been separated with the compressor, which is anyway there, and you put a receiver over there, and we have used the pulse tube inside here. So the gas will be passing through the regenerator, going to the pulse tube, and inside the pulse tube, the high pressure will be moving, expanding in a very high expansion, and whatever the expansion process, whenever the cold is proceed, you quickly take it away in a heat exchanger, where this is where your cold finger is there, and when the hot gas coming out of the system will come here, will get, because of the heat, it gets slightly compressed, will go through the heat exchanger, all the heat gets absorbed here, and again further goes to the compressor section. So the vibration from the compressor anyway avoided in GM cryocooler also. The functionality of this valve mechanism is completely isolated by putting the heat exchanger away from that. And this pulse tube, there is a pulsating flow will happen. That will give a kind of an expansion compression operation, which will lead to reduction in temperature. By doing that, it's almost removed all the vibration. So this is the only change in happening in this thing. This is based on these thermodynamics involving oscillatory pressure changes. So this is the whole idea of all this cryocooler. Now we'll see how this can be applied in the application, various application. We can use this cryocooler based for liquefaction of liquid nitrogen. You have a compressor and the flexible line, head is hit on the top, and when the nitrogen gas comes into here, get condensed and drip down. Okay, the liquid. So this liquid helium, we are using GM cycle. We can also use the GM's cryocooler, two-stage cryocooler for producing helium liquefaction by using, because the size is not so big compared to, so just relevant figures are given. So the first portion will go to something like 20 K, second will go to less than 4.2 K. So the gas, helium gas comes in, get into the system, will condense and then fall back here. So here, these are only collecting vessel. It is not an equipment. So the vibration of GM cryocooler is not so much of difference here. Okay, it can be tolerable. But if you are using for a specific application on the head of your this thing, then it becomes a problem. So you have a large cryocooler also possible, which can go up to 20, large in the sense now I'm coming from the miniature to the large, not from that commercial to here. So it is a 20 liter per day. One GM cryocooler is fitted on the top. We can produce 20 liter per day, and we have that is in ICER Pune. We have a 3 JA column. Just scale up, they could do 60 liter per hour. Sorry, 60 liter per day. So by jacking number of thing, you can put 4, 5, depend upon your thing. You can just scale up the way you want. Okay, up to 5 I have seen, but if it is there, then it will be next will be. So either all the 3 will be running, either 1, 2 will be running. Depend upon the load, it will automatically done. So basically, this is the large cryocooler in the kind of smaller application compared to TFR. This ICERs, most of the ICERs have gone, and ICER Trivandrum, ICER Pune, ICER Mohali, and many institutes where the demand is not so high like us, and then they can afford such a small plant which can still go on with that. Okay. And we can also have a helium liquefaction, the pulse tube cryocooler. Okay, this is also something which can produce from, you have a long range from 15 liter to 80 liter per day. This option is there. So depend upon, again, the pulse tube head will be changing over period. Here, you can also connect to a reliquefier post. Okay, that's what means. It's a liquefier pulse tube. Now you can also use the recondenser. It means that it's an experimental cryostat. It is filled with helium. When the gas is boiled up, you just recondense it from whatever the load. It's not coming from room temperature to 4.2 K. The boil off gas quite maybe load maybe up to 40K or even lesser that it just from 40K to it just drips back. So once you fill the liquid helium, whatever the evaporation gas, it gets re-liquefied and then condense it back. So here the mostly they use the pulse tube cryocooler in the sense that because it is part of the experimental system, the cryostat may have a problem. So to avoid that, normally they go for the pulse tube cryocooler in terms of re-liquefaction unit, which is part of the system. So this whole unit, they get it, you just insert into the duvar and connect it. So it starts recondensing it. So that current technology, because of the helium demand or the expensive helium, people wanted to avoid to go for the ever cooled or cryogen free load. It's basically once fill and then forget kind of thing. Okay, so similar way it can go, but that liquefaction rate or the re-liquefaction rate is very small, 2.7 liter per day, because the cryostat itself will have some 30, 40, 50 liters. So the boiler would be something normal would be about 5 liters per day, or maybe less than that, depending upon the experiment, high fill experiment or low fill experiment. So this can have either a 2.7 liter to 2. So this is a typical what you get it in the market. Okay. Now we're coming to this Starling cryocooler, not the pulse tube, the Starling cryocooler, not the GM. It's a built-in cryocooler, very in a miniature type, where it can have a hand-cooled cryocooler-based infrared camera, which is widely used in the military operation. The border people, they are still using, and India has also developed a few with an IT collaboration, Bombay collaboration. So basically it's less than 3 kg, and it again uses a small bottle which can be changed with the gas. It can be either air, nitrogen or high pressure gas, whatever it is, and a small motor based cryocooler is also there. So everything is possible. So this can have an 8x zoom, and the night vision, of course, it is there. It detect the measurement range is 12 kilometer, and the human is detection about 5 kilometers. So human detection can be very precisely seen with the infrared thermal cameras. Okay, and we also have a very tiny 2 inches cryocooler, which is an bottle. This is produce a compressor, and then it can have the pulse tube will be there. So this will be kind of an different type of compressors which can load it and can produce low temperature. And for the optical application, this is a 0.2 watt. It's only less than a kg. We can produce 77K to 300K. The optical sensor you connect with this Starling cryocooler, which can go up here. And then you also have the specific experiment specific cryocooler, because this head can be changed the way cold finger can be changed to suit that experiment need. Basically, it can go down to 80 Kelvin within 5 minutes, and its weight is less than of a kg. So such a things also exist with the proper compressor. Okay. And also we have come to the end of it almost, like we also have a Hankel cryo probe with just like a pencil. In fact, it comes with the pen cap. You can use a pen and remove and use a cryo probe. It's just cap it and then do it. So here is like a normal Starling cryocooler, normal JT cryocooler, and this is the small bottle in which the gas is filled, and filled with 55 bar of nitrous oxide. This particular company is 23 gram weight is a total gas cartridge is that it can produce about 185 watts, which you feel. So I have a small video from this same company. So this cryo tip, or they call it the probe tip, is used for a delicate skin, can be used near the even eyes. That's what she said. And so this expansion will give some quick temperature drop, which can be used for the quick healing of wounds or the tumors to freeze off and cut off. Mostly it can be used on the animal, as well as this video shows most on the animal. And this is the bottle. That's what he's saying. Then another thing. So these are the various tip you can select, and these are the bottles. Okay, so the bottles are so tiny that can be fixed into the system, and you can buy a cryoprobe with so many cylinder filled with gas. That's empty, that connect it and then do it. Okay, so now this also used for cryosurgery in land. Okay, here They may be using liquid nitrogen or the liquid nitrogen vapor or the Joule-Thomson cryocooler or the Stirling cryocooler. So mostly they use it because it is an operational area that it can have a fixed pace. So you can afford to have a kind of a cryocooler, and then only the cold nitrogen gas comes in here, or you have a nitrogen just above. So the liquid nitrogen can come in. It gets expanded here, which also have some low temperature. This probe, it will be touched to that part where you want to have an bloodless surgery, so tumor to be removed. So basically, a small endoscopy operation. It's very tiny. You can have, it's like a bloodless surgery. So you can cool the tumors or any part, then you can cut it off, break it off to the thing. Okay. So this is called the cryotherapy and cryoablation. These are all the retinal used very heavily. I have a small video animation showing that to remove how this cryoprobe using liquid nitrogen vapor used for the kidney tumor removal. So in this one, the cryoprobe is pierced into this thing, and the liquid nitrogen or the nitrogen cold vapor is flowed here. See, nitrogen vapor is not going out of it, is sealed one. So only by conduction that low temperature is come in contact with the tumor, and the tumor slowly you cool it long enough so that the freezes the entire thing slightly above that. Then after some time you heat it. Okay, by heating it, just stop the nitrogen flow, put some warm gas inside, so it gets warmed up. Again, refreeze it, again heat it. So the repeated heating and thawing makes that cell die, and whether you can cut off, you break, and then so this kind of an endoscopy operation is there. That once it is there, you can just remove the thing. So this is a very, very popular way by which the operations are done using the cryocooler so thing. So now these are the engineering. Huh? It is there, yes, it is there. Yes, yes, yes. It is there because it's very popular nowadays. This correct. So they used to have many of the things where the probe can go in endoscopy operation, where there is a delicate location is there. We can go for this one. Okay, and then you can break and do it. Okay.
The thing is, are there prior to the design, especially for protein condensates?
For the protein.
Protein
No, see, I'm not sure about a very specific equipment. I said that depend upon the temperature, what they need, and how much is the cooling load. Because not only the temperature, basically it comes with a word called the cooling power of it. It means that if a particular has a cooling power of 1 watt, it means that 1 watt at 77 K means if I put a heater of 1 watt also, the temperature remains at 77 K. Okay, so if it exceeds, it may drop. So the cooling power and the temperature need, it's depend probably possible with that thing. So now I wanted to just say the final location that how that engineering marvel of such a large plant where you can see the ratio of the people and long operating like TIFR and other places we have it to come to a place of like a crackler to the pencil or pen level. Everything exists and with all has a different way of application like what you mentioned asking about this thing. And I'm coming to the final slide, which we have started with that. Is all the things necessary or not? I don't think that none of the thing is necessary or mandatory to do that. What it is, the big chill do come in a small package and it do fulfill the requirement. So it's a substance, not the scale matter really with that. And thank you very much for your kind attention.
Very nice indeed. So, basically, I hope everybody is convinced that engineers are contributing not only to something, making something, but also to the great way, healthcare and other space stuff. And there are no limits.
Yes.
Engineers know no limits, right?
So far it has come pen level, so probably may go down also.
Very big machines. Engineers have successfully miniaturized it and make it available for very different type of applications. So that's the thing. So let's thank Srinivasan ji.
Thank you very much.
Stop the live stream, have a tea break, and then.
Sir, any questions from the Zoom? Okay, done. So you people have any questions also?
So
yes, yes, some.
But
okay.
Take a break. You also have some chat.
Okay, okay, right.
And
then we'll have chai and wine. Yeah. Right then. So, thank you very much.
Thank you for all. You guys please go ahead. आई क्या क्या ले लिया?
क्या?
आई आई क्या ले